Today we start with the new topic. Topic number 3, frequency response of dynamic system. This has been around us for a long time, so probably most of you are already familiar with this frequency response. If you know the frequency response of something, then you know all the dynamics about that thing. Okay? It provides all the information about dynamic characteristics and the steady state characteristics, and it also provides all the necessary information to design for the controller. But that is only true for the linear time invariant system. So you know what linear time invariant system is. Linear time invariant systems, what I have said is absolutely true, but we are not interested in that. We are interested in non-linear dynamic system. So maybe we are interested in non-linear PWM converters. Okay, so even though you have the deep knowledge about these linear time invariant systems, that cannot be directly applied to the PWM converters. So I'll explain, or we study how to apply this frequency response concept to the nonlinear PWM converters. Okay, so what is the implication of frequency response of PWM converters, and what is which is the validity of that approach, and what is the limitation of that approach will be addressed. Okay, that is also important. And so if you understand this topic number 3, you can apply all the knowledge you have on the linear time invariant system. For example, Laplace transformations, transfer functions, and root locus, Bode plot, Nyquist analysis, so on. They are the best amount of knowledge, but you cannot apply that directly to the PWM converters. So we need to do something. So basically, we want to extend this concept of frequency response strictly defined for the linear time systems to the nonlinear PWM converters. That is the subject of this topic. So it consists of 3 subtopics. So first one is frequency response of linear time invariant system. This might be the review for the most of you. So we review the basic things about the frequency response of linear time invariant system. Then we discuss the frequency response of PWM converters, and we address the validity and the limitations of this approach. Okay, and finally we will discuss frequency response of converter power stage. So you cannot do this directly, so we need something in the middle. So we should use linearized small signal. Later on, I'll explain the small signal things, what small signal means. So what is missing here is linearized small signal model. We'll be using the linearized small signal model of converter power stage to investigate the frequency response of converter, PWM converters. Okay? So this is the outline for this topic. So first, we discuss the well-known frequency response of linear time invariant circuits or systems or networks. So by definition, suppose there is a linear time invariant systems. So in the input, you apply Vi1t. Then you will get 1t, right? If we multiply k here, then output will be multiplied by same k. Okay, this is called proportionality, characteristic of linear time invariant system. And if you add another input, suppose you add vi to t, then response of that is this one plus vo to t. Okay, if you apply this one, you will get this, and if you apply this VO2, then you will get this, and you multiply this VI1T by K. Response is simply this one times K. Okay, so this is the proportionality, and these two things is called what? Superposition. So any system which is called the linear time invariant system must satisfy these characteristics. Okay, this is the definition of linear time invariant system. So for the moment, maybe this lecture will be talking about only linear time invariant systems. So sinusoidal response is defined in this manner. Sinusoidal response is steady state response of linear time invariant system to a sinusoidal input at given specific frequency. We are talking about just one sinusoidal wave at particular frequency. We change this. So VIT is sinusoidal input, then output will be what? Sinusoid. Okay, shape remains the same, and the frequency remains the same, but two things can be changed. First one is magnitude can be changed, and this phase can be changed. All right, so this is the typical way of drawing or explaining the sinusoidal response of linear network. But we are not only talking about this linear network. This is more important. Linearized network. Something is nonlinear. It does not obey the proportionality property and the superposition that I want to do. You locally linearize the nonlinear system and apply that. Apply this concept to this linearized network. Eventually, this is our goal. PWM converter is nonlinear, so this is PWM converter. There is a PWM converter. You cannot apply the knowledge about the linear time invariant system directly. Then you do something is called modeling. Then you will get small signal model, which can take all of the previous knowledge on the linear time invariant system. Okay, so this is the approach you're going to take. So this modeling process is extremely important. The purpose of modeling is very definite and clear. We want to use our knowledge on the linear time invariant system to the nonlinear system with minimum error. Okay, so the validity and limitation will be addressed. So this will come later, maybe next topic. But still, we want to discuss about the frequency response of nonlinear PWM converters in some sense. Okay, I'll explain that in the next slide. So for this case, this is the input and this is the output. The change between this and this ratio of the VO to VI is called gain response or magnitude response at omega naught, at one specific frequency. And the phase delay, this has zero phase and it has this phase delay. This phase delay is called the phase response at that particular frequency. This sinusoidal response is generalized to frequency response. Okay, so this frequency response curve or frequency response is coming from the definition of sinusoidal response. When we are talking about the sinusoidal response, we assume we are interested in only one at what frequency, at the specific frequency omega naught, we measure this one. This is gain response or magnitude response, and measure this one. This is your phase response. And you continue doing this measurement here, and you squeeze the distance between your measurement period continually. Then this space will be reduced, and you will get this continuous curve. This continuous curve is called frequency response curves. This is the magnitude response curve, and this is the phase response curve. Okay? There is many ways of expressing or portraying this frequency response, and we'll be talking about the special format proposed by Hendrik Bode, which is Bode plot form of this frequency response. Is the most important and extremely useful for the analysis and for the design as well. Okay, so maybe we first talk about the measuring the frequency response of anything. Okay, this is the equipment called impedance analyzer. This is called impedance analyzer, but when you are talking about its functionality, this is more appropriate name, wideband, and frequency tracking gain phase analyzer. So, okay, this is the more appropriate name. I'll explain this later, the meaning of this one, when we are talking about the frequency response of PWM converter. Okay, and we will discuss how to measure frequency response of PWM converter and the implication of that and the limitation of that. This approach is different from the prevailing approach and my approach in the past. In my book and all the textbooks and in my all the previous lectures, I explained the small signal model first, how to obtain the small signal model, and from the small signal model, I explained the frequency response of that model and the relationship between those results to the PWM converter. Okay. This time I changed the order of explanation. Maybe this approach can be called bottom-up approach or top-down approach. I don't know which one comes first. Okay, so we'll discuss the measurement result, simulation result first. Then later on, we'll be discussing the modeling of PWM converter in the next topic. Okay, so first I'll discuss the experimental and computational evaluation or measurement of frequency response of PWM converter. So this is the equipment suitable for that purpose. Okay, this is called impedance analyzer. So this is an extremely simple application of that. So you have some circuit and you want to measure input to output transfer function of this simple circuit. Okay, then you can use this impedance analyzer, and impedance analyzer is generating the sinusoidal waveform with variable frequency and the magnitude. So you can set up the range of the frequency sweep, and the magnitude can be changed during the operation if necessary. Okay, so suppose the sinusoidal waveform is coming out here from this output terminal, and this sinusoidal waveform is going this bad location. It should move down. So this is the sinusoidal input, and the sinusoidal input is here, and the input is sense this proof. So this is the one proof. There is another proof, and another proof is connected to the output port of this network. Okay, this is an extremely simple network. We know the transfer function of this already, but suppose we don't know what is inside of this block. So this is can be considered as the black box. Okay, then you put sinusoidal waveform, and the sinusoidal waveform is coming out. That those are measured this channel 1 proof and the channel 2 proof, and this equipment will generate the curves, this T ratio of this input two output signals and the phase difference between input to output signal. That is the magnitude curve of transfer function, and this is the phase curve of transfer function. Okay. There are many variations of this equipment. The legendary one is, this is very old, 4194. HP is, it stands for Hewlett Packard. They are the brothers, okay? There are two brothers, Hewlett and Packard. They established a company and they made this equipment. And later on, this equipment was very expensive. You will see that later through the video. This is something else. After that, the one England guy, he simplified something, digitized something, and this is this version is maybe first generation and the second generation. And maybe you know this guy. He is my colleague, and he is very famous in the business of PWM converters, Raymond Bode, okay, and he adapted this scheme and he modified this and he miniaturized this. The equipment is called AP120, and recently some company developed same equipment but much smaller and handy size and many other functions called Bode 100. So maybe this one is the latest version of it and will be come up with the better version later. But this is very useful and versatile equipment. But I saw many people, many students in the university, top universities in Korea, SNU, KAIST, and other place, they use this equipment as just impedance analyzer. Okay, they use this equipment, the value of inductance and the value of capacitor, something like that. Okay, so this tool is very big, but what they are doing is very huge, very small. Okay, very trivial. Right? This device can measure any transfer function, loop gain of feedback system while the system is operating, and so on. Okay? So we'll be using this equipment to measure the transfer function of linearized form of transfer function of nonlinear time-varying PWM converter. It really doesn't matter. There is just some digital control or digital board. Still, you can measure this transfer, the frequency response in the Bode platform. Okay, so we'll be discussing that. And I already went through this. The output port inject the input sinusoid while sweeping the perturbation frequency and sometimes changing the amplitude of the sinusoidal input, and channel 1 and channel 2 extract the sinusoidal component at the perturbation frequency. This is important. Here input is sinusoidal waveforms, output is sinusoidal waveform, but it really doesn't matter. It is some strange waveforms. Okay, you put sine wave here, and this will change the output in strange way. But this device extracts the sinusoidal component from the output. If this signal is periodic, there are Fourier series, so it extracts the fundamental component Fourier series, and they compare this sinusoidal in and the sinusoidal component of the output voltage and generate this. There is a typical way of getting the approximated sinusoidal response, frequency response of nonlinear time invariant system. Okay. Another thing here. Suppose you have this device. You don't know inside of this. Okay. Somehow you want to know the impedance of this device. All right. So you need to measure V across this device, and you measure I, okay? Then you divide V by I, then you will get the GI seen here, okay? Seen through this device. So this will be the input impedance of the device, okay? Then use this equipment, and this is the output. This is sinusoidal waveform, okay? And sinusoidal input is passing through this. This is 1 ohm with very high precision. So this is exactly 1 ohm. So the voltage developed across here is I times 1 ohm, which is I. Okay? So this port is measuring voltage, but it is measuring the current. Then you measure. Then this channel number 2 measure voltage here and get the ratio between them. Then this curve is the magnitude curve of input impedance of this device. And this is the phase curve of input impedance of this device. Okay? This is also very primitive way of doing this. And most students, they don't know how to measure this. Even the vendors of this equipment, they put these things in box, some fancy box, okay? And they charge it for the $500 or $1,000. They are getting money out of this simple box, okay? So don't buy those box and you use this to measure this input impedance of something, okay? But this is also extremely trivial application. Use of this equipment. This equipment can be many other things, okay? So we'll be discussing that later. But somehow I'd like to show this. This is the curve measured in this manner to characterize the input impedance of inductor and the input impedance of capacitor, right? So let me go through this in some detail. Okay, so this is the curve of inductor. For the inductor has inductance L, and it has some winding resistance R, L, and it has some inner winding capacitor, which is very small. So inductor is really the combination series connection of 3 passive components. At some frequency, this L is dominant. They can be ignored. At the frequency, this R is dominant. You ignore this. And at some frequency, this C is dominant. Then you should ignore this. Okay? So if you measure the input impedance of this in this manner, at low frequencies, this is dominant. So at low frequencies, this is the SL. This is Bode plot of this function, differentiation function. This is SL. And slope in this region is 20 dB per decade. Okay. At this frequency, it goes up. If you have this sharp peaking, this Q of this circuit, this is the resonance circuit. LCR resonance circuit, and this is the high Q, very high Q, and this peaking, suppose this is the continuous curve, then this magnitude is 20 log Q. Okay, so Q now is very large, so peaking will be very large. Okay, this is a magnitude curve, and take a look at the phase curve, which is this. This maximum value, maximum limit is 100 degree. So actually this is 90 degree. This is 90 degree. So this is the inductor. If this is the ideal inductor, this curve goes forever like this. Okay? And this part, equation of this transfer function is simply SL. Okay? Then this is the this is the dB scale. So there should be a this line is 0 dB. Okay. Then value of the inductance can be measured this crossover frequency. Okay. You have inductance R. This 0 dB crossing frequency is 1 over L. Why is that? When you put this 1 over L here, this becomes 1. Right? 1 is 0 dB. Okay, so this is from this measurement you can know the inductance of your inductor from this value. Okay, and at this peak what will happen? You have this reactance and this reactance, this is inductive and this is capacitive. At this frequency, they cancel each other. At this frequency, impedance of this cancels with this, and the remaining value is what? This is R. If you check this R, this is the value of your, let me use this color. This is value of, oh, not this one. This one is measured here, L is measured here, okay? And after this phase is 90 degree, and after this phase is minus 9 degree. At this moment, at the peak value, phase is what? 0, right? So this horizontal line is 0. So at this point, because this becomes resistive, phase is should be 0, and after this, the slope is this one, SC 1 over SC. It becomes capacitor. So for this frequency, it behaves as an inductor, and this frequency, it behaves as a resistor, and after this frequency, it behaves as capacitor. So this is a parallel combination of L, R, C, but at different frequencies. It behaves as the desired inductor, but at higher frequency, something else. It becomes a capacitor at high frequencies. At this particular frequency, it becomes resistor, and this particular frequency is, we evaluate this, okay? The magnitude of SL is the same as magnitude of the SC, 1 over SC, okay? Then this frequency, at this frequency is 1 over square root LC, all right? So S is omega, we are talking about magnitude. So at this frequency, they becomes the same, all right? So this omega naught is easily calculate this. So simply this is the 1 divided by square root LC, and this is this 0 dB. Frequency of this one is, again, this is 1 over C. So this value is 1 over C. That now you measure all over this, right? This is the proper way of measuring this. You have LCR meter, right? I don't know what LCR meter is doing. So maybe generating garbage and garbage. Okay, I really don't know, cannot understand the principle of LCR meter. In LCR meter, you select the operational frequency. I don't know what that means. Okay, if you have this parasitic component, you want to have circuit behavior of this with some strange waveforms, then use this. This is the linear circuit model. At some frequency, this will be dominant. So maybe the inductor is talking here, and the resistor is talking here, and the capacitor is talking at different frequencies. Okay, so this is one thing. And capacitor is the same. This is the input impedance curve with capacitor. Of course, you have capacitor. So capacitance is large, and this is ESR of capacitor. ESR of capacitor, and it has some resistance. Inductance here. So this same LCR circuit represents the practical circuit model of capacitor, and this part over here is at low frequency. This is dominant. Okay, so this is again, this is 1 over SC curve. At this frequency, this becomes RC. This is the ESR of the capacitor. Okay, so for this is the typical way of measuring the ESR of capacitor, which is very important. Okay, so this is ESR of capacitor at high frequencies. This is the dominant. At low frequencies, this is dominant at this particular frequency. L is dominant at high frequencies, and this is the slope. Okay, so this is minus 20 dB per decade slope, and this is plus 20 dB per decade slope. Suppose the 0 dB line is located in the middle. somewhere here. Then this value, this frequency, this is 0 dB, and this frequency is 1 over C, same as previous discussions. And this is this X value, radian per sec value corresponding to this 1 over L. Okay, and this is, I said this is the RC, so you measure this all together with this simple measurement, right? Typically, this is some kind of a film capacitor, which is very good capacitor. Okay, if you use the MLCC, multi-layer ceramic capacitor or something else, ESR is very small. Then this value should dip down like this. Okay, this is high Q. And this ESR, RC is very small. So this is the MLCC. And this case shown here is film capacitor. This is also expensive one. All right. The most cheapest one is the electronic capacitor, which has polarity plus minus sign. All right. At that case, Q is very small, less than 0.5 over 1. So here we have double pole. This second order pole, double pole. This is double pole with very high Q and medium Q. If Q becomes less than 0.5, double pole split into two poles, two separate dual poles. So for this one, this capacitor, the cheapest capacitor. Let me use some bright color. This one, okay. Now Q is very small. Less than 0.5 or something like that. And two dual poles split in the one double pole split into two dual poles, and one pole is here and another pole is here, and split occurs in equal distance in here. In this is a semi-log scale. So in this screen and length of this should be the same as this. Okay. I think we went through this in the previous semester. That was the control course. Okay, split is really happening here, and the ESR is relatively large. Okay, and it does not have any this second order characteristic here. Let me show this. Okay, this is the interpretation of this measurement using this equipment. I'm man of my word, so I'm proving what I have said. This is the impedance analyzer. This is the HP 412494. Okay, this is classical one. This is the inductor. So inductance is this one, and this is the resistance of winding. And this is a jig. Jig is the one I explained. It basically contains good contact clip and 1 ohm resistor. Right? This cost $1,000 at that time, maybe several $100. Right? And measuring this. Okay. So he was my student. Measuring this. This is a screen I showed, and this is the maximum value of phase, and the sinusoidal waveform is injected. The waveform is not shown here, and this is sweeping. So this curve looks like this. So it starts from this is a very low frequency, and at low frequency, this curve, movement curve is very slow because it injects low frequency, right? And it finds the steady state value of steady state response and something like this. So it takes some time and go up. And this slope is 20 per decade. and I don't know where is 0 dB. 0 dB somewhere here, and goes like this. Okay, so it goes like this. So this phase is 90, and this phase is minus 90. This phase 90, minus 90, and this, okay, this is the graph provide L, NC, and RC, all right? And this is capacitor, this is a film capacitor. This is big, compared to it's the capacitance and the voltage rating. So it has good performance for the high frequency capacitor. And I'm measuring this. And maybe this equipment stored some data, so maybe it plot very quickly now. You will see this soon. Come on. It will come. What happened? Stopped? Oh, I see. Right? So this is capacitive curve, inductive curve, and this value is ESR. Okay? This is a good one, right? So if you have, oh, this is bad one. This is the cheaper, not bad one, cheaper one. This is the electric capacitor. Then it curves may looks like this because Q value is very small. Q value is inversely proportional to the ESR. Okay? High frequency capacitance, high voltage capacitance. This, right? So this is capacitor just until the frequency below this line. After this is a resistor, and in this frequency, this is the inductor. Okay? So I don't know the frequency here. So you cannot expect that device will work as a capacitor and at high frequency or medium frequency range. Okay? So this information is rather important. Okay, so this is the equipment I was talking about. Okay, this was very, very expensive and very fancy one. Right? So it has, they said this is the best equipment in terms of the analog electronics skill. All the skills are embedded here at that time. And I think this is the outer product because this is too expensive, too heavy. So they come up with new things which use the digital technique. Okay, this is a purely analog circuit oriented equipment. They are no longer producing this. And when I came here, Korea, about 35 years ago, there were several equipment in Korea. Then our lab has one. Other than mine, all of them are broken, not working. They don't know how to use this, and they didn't know the value of this equipment. They just used to measure some impedance or resistor, something like that. Okay. Later on, you will see this equipment can measure all the transfer functions, nonlinear, time varying, digital, regardless of the nature of the circuit. You measure the input-output frequency response. Okay, that is the very important fact. Okay, and very useful fact. All right. So this was the plot I was explaining here, here, and here. All right. Okay. We measured the impedance here, right? But usually we don't have to measure. Okay. But sometimes we must measure. That is the case of if you do not know the small signal model of the converter. Okay, suppose you don't have that knowledge yet. later on you will have the complete knowledge about that, then still you can measure and you can interpret it. Interpret the result, all right? But if this circuit